more cassettes within a specified area of time than is currently able to do with manual sorting. And it will also increase the traceability of certain processes within the lab. So we have formatted this as a series of research questions. There is one main research question, and then there's 3 sub-questions, which all feeds into the main question. The main question is, how can the pathology workflow be streamlined by implementing automatic sorting mechanics for cassettes? The first sub-question is, how can the implementation of a tracking solution using optical character recognition improve the efficiency of sample processing at the pathology lab? The second question is, how does the accuracy of cassette detection vary when using different pre-trained image processing libraries, specifically edge detection and the East neural network? And the final question is, what does the effect of the proposed digital solution have on the time it takes to sort cassettes compared to the current manual sorting methods? So I had a look at what alternate solution exists to this problem. And there are currently solutions, however, their technology is fundamentally different from the one I will be proposing. I could find 3 different companies producing equipment that allows you to scan the data matrix code of cassettes in batches. However, these all require large, expensive proprietary machinery, which means you can only scan 1 cassette at a time. They are, as I said, they take up a lot of space, and you need proprietary storage hardware to use these machinery, which means the pathology lab will then need to keep purchasing these proprietary storage racks, and if they stop to be sold, that would of course pose issues for the lab. However, for my research, they have provided a few case studies, mainly on the ARCA system, that does show that there are indeed some benefits to digitizing these processes. It does in fact improve the control of material management. It does increase traceability and patient safety, and it saves time by reducing manual sorting activities. And it also has the chance to reduce the chance of human error in sorting, which, after talking to one of the lab technicians, I understood was an almost daily occurrence. Certain cassettes are placed wrong in sorting, and it will then take hours to retrieve and find them if they need to use it again, which can be a big problem. So, as I said, these rely on batch data matrix scanning. I will be using optical character recognition. So, the cassettes I showed you earlier, I will be scanning the text of those, and using these 2 tools, I should be able to do that. So, what are these tools exactly? The first is Tesseract, which is an OCR tool. That means it's able to extract text from a specific image. It's actually quite an old tool. It's originally proposed as a proprietary software by Hewlett-Packard in the 1980s, specifically in 1984. In 2005, it was released as an open source project, and in 2006, it was sponsored by Google. Version 4.0 is a major revision for the project. Here they implemented long-term, short-term memory neural network methods to improve their processes. The current newest version is 5.2.3, I believe. It released in April, and I used a slightly older version for the project. And this is still being continuously developed and updated today to keep up with the cutting-edge technologies and the newer standard. The other neural network I'm using is called EAST. That stands for an efficient and accurate scene text to texture. Tesseract is very good at reading text. However, it suffers from finding text. So if you have an image with 100 cassettes, it doesn't know where to start, and it's not performing that well. To do so, we use EAST. EAST is able to extract the coordinates of text on an image, and by doing so, it's able to capture each individual cassette as a separate image. So one image will turn into 100 smaller images, each image featuring 1 cassette. EAST is released in 2017, and it's much faster and more accurate than the current competitors at the time it was released. I'll also talk a bit about currently existing and ongoing projects in the pathology lab very briefly. There is currently a process mining project which aims to combine the data mining and process analytics and receive some valuable information from the currently existing laboratory information system logs, with the overall goal of reducing the cycle time for each specific cassette. So the cycle time is the time it takes for 1 cassette to go throughout the entire lab and be processed from the time it enters the lab until it is finished processing. However, it's hard to do it when certain parts of the data from the system is missing, and this is one of the things I'll be looking to address here. Another project is another master thesis in 2021. Here they tried to do they tried to do business processing simulation on the data from the pathology lab. Again, similar issues were encountered with missing LES data, which makes it hard to make a complete model that simulates the entirety of the lab. I'll quickly talk about design science research, which is the method used for this thesis. The artifact has been designed according to DSR guidelines. It's been an iterative trial and error process with 2 major milestones, and the artifact is evaluated according to the same design science research guidelines. and the evaluation of the artifact is compared with real-world metrics gathered from the pathology lab itself. So what exactly does the thesis contribute? There is actually quite a broad amount of contributions from this thesis. Firstly, there is the real-world performance metrics, which have been measured in the lab. There's also the artifact evaluation and the artifact itself, which has been created through a series of meetings, 7 meetings with representatives from the pathology lab to gather feedback. There's also been a presentation for UIB and the Intelligent Information Systems group to gather some more domain knowledge about specific issues. And of course, there's been a trial and error process when developing the application itself, which have shown some interesting data. There's also a REST API and a user interface. That's essentially what the main artifact is consisting of. I also talk a bit about how to interface with the process execution engine and how to implement the artifact in the current pathology lab and the workflow. In addition to these contributions, there's also been a paper submitted to the International Health Data Workshop. This was written by me and all my supervisors and co-supervisors in collaboration. The paper has now been peer-reviewed and it has been accepted, so it will be presented and released this summer. Yes, let me talk a bit about the main artifact. So the main artifact is the image processing application. Essentially, it consists of 2 other sub-artifacts, which is the REST API and the graphical user interface. But overall, the artifact is capable of specimen tracking, of locating, identifying, and extracting text, of storing sample location, cassette text, and metadata about where and when these cassettes were placed in certain locations. And it's able to tell when samples have been retrieved and placed into storage through scanning these cassettes, either in batches, or it can also scan them one by one if that is needed. Let me talk about the first part of this, is the REST API. This is the processing model responsible for the image processing. So it takes the image as an input, as a URI, Uniform Resource Indicator identifier, and it processes the image link together with a tag to use either the east or edge detection neural network. I figured these would be 2 interesting things to compare because edge detection is a very traditional mathematical-based way of finding the cassettes, whereas east is a neural network, which is more cutting edge and might give some interesting results, which will be seen later. Yes, and the results from this API is returned as a JSON document. Then there's the graphical user interface, which was required for some manual error correction. The REST API wasn't able to perfectly capture all the aspects of the cassettes. However, unfortunately, user interface has not been evaluated. That would require to implement it in the lab. There was not enough time to do so during this thesis, but it's maybe a viable future option for something to look at. So yes, as you can see, it has quite a lot of features. It can search for specific cassettes. You get a list of cassettes that are on the image, and it allows you to add and remove certain features to ensure the data is complete. So how is this built? It was built through 2 major milestones. The first was the MVP, the minimal viable product. This was very basic. It had, as you can see, it's on the right side there. It's the very basic user interface. It has no advanced functions, but you were able to process and see the cassettes. It worked through processing 1 single image, which I stated earlier, Tesseract is not good at, so you can see the results are significantly worse. The second milestone, I implemented both east and edge detection, which significantly improved the performance compared to base Tesseract performance. And also I improved the user interface massively with some features which would be convenient and make manual error correction much easier. Yes. So how can this system be implemented in the pathology lab? Here you can see a PetriNet. It's the same one as before. This is using the LES data, and you can see the new red transitions, which is where the system could be contribute with current data, which is currently missing. Most notably is the archive. You will be able to see when blocks are placed and retrieved from the archive. That could be very interesting to see how often blocks are retrieved. That's current data, which I don't think they have much of. Yes, and in addition to this, there is also an overall system architecture, how this artifact could work with the current process mining project that's ongoing. As you can see, both data from the LES and from the image processing is able to create more advanced event logs. These can then be used for process mining, which can be used for simulation, which can be used for improving the workflow of the pathology lab. And this is an iterative process which can keep on improving itself and lead to further improvements down the line. Yes, evaluation. So how was this artifact evaluated? Well, the artifact was evaluated according to design research guidelines. There is mainly 2 evaluations in this thesis. The first one is the evaluation of the application performance on cassette scanning. So this shows how both edge detection and east differs when scanning cassettes, the significance between accuracy and OCR detection, data such as that. And also there will be a comparison of data from the lab, how long it takes to sort cassettes in the lab, compared to how long the artifact uses on sorting these data and logging this in the system. Yes. So how was the data collection for the manual sorting in the lab done? It was done using natural observation technique. I spent over an hour with a lab technician in the pathology lab. The first minutes was spent slightly on an interview. I asked some questions, I got some answers about things that were unclear. Then the next last part of this was 1 hour of observation where I observed the lab technician work on sorting cassettes. Every 10 minutes I wrote down the results of how many cassettes had been sorted in the set amount of time. And this was done on an entirely random day. I do not think, or the lab technician should not have known I was coming, which means that performance should have been as normal as possible. That was the goal of it. And to compare this to edge detection east, we need the aforementioned manual error correction, because you can't compare a perfect sorting to an imperfect solution, of course. As for data from the application, how was that collected? Well, most of that was collected from the application output itself. There was some manual compilation and counting of how many cassettes were in images, etc. And of course, the images were not altered in any way, but they were selected for clarity. So we did not input any blurry images. We made sure that the images we tested on were of a decent or acceptable quality. They were captured using an iPhone, which is unideal. Ideally, we should have access to higher resolution camera, but we did not have access to this during testing, which means that we had to work with what we had. I'll talk a bit more about that later. So I'll start off by presenting the results. Here you can see the results from the application performance. This is the difference between east and edge detection on scanning cassettes. As you can see, the edge detection is slightly lower than east, but they're both performing adequately. However, this is healthcare data. You want the performance to be as accurate as possible, especially if going for a fully automatic solution. For a semi-automatic one, which requires manual error correction, it can be debated that these are decent results. However, there's of course a discussion to be had there. As for OCR performance, you can see there is a significant difference there, and this is very interesting considering both of them are using Tesseract for the OCR. This is based on how many of the images in total were recognized, how many of these were recognized by the OCR program. I think that the reason for the difference being so big is due to the cutout of the images. So edge detection captures the entirety of the cassette, including the data matrix code, whereas east only captures the text part of the cassette, which means there's a significant difference in the noise in the images. And I believe that could be what's causing this, but more testing has to be done to verify or show these results. Yes, and also with using the neural network, you will see a significant amount of runtime increase. Keep in mind that east is running 2 neural networks, first east and then Tesseract, whereas edge detection is only Tesseract for neural rounds. It's more traditional mathematics for the edge detection algorithms themselves. And that does change the time. However, keep in mind that a pathology technician would not be locked up for 30 seconds when doing this. They could do other tasks, prepare a new tray for scanning, for example. Yes, so what are the results from the in-lab trial? This is when I measured how many cassettes were sorted in a set amount of time in the lab. So sorting times, as I said, were collected for 1 hour. And you can see that the lab technician I was with had over 17 years of experience. This gives a good image of what an experienced sorter could sort like that. But as you see, there is a lot of variance between each 10 minutes. It's as low as 44 for one and as high as 173 for the other. The reason for this is due to major archiving restructures. As I said, they can't compromise space because they don't know the size of the blocks they receive in the grossing step. The only way to know that is by scanning them before you start sorting, and that is of course unideal. That would take too much time. So this means that occasionally the entire archive has to be restructured, things have to be moved to make space, and this very, very much slows down the sorting process. Of course, I only had 1 hour to take measurements. It would be very interesting to take measurements for a longer amount of time and see how the results develop. Yes. So application sorting performance. This is how the application worked when sorting. As I said, some manual error correction was needed. As you can see, due to the poor OCR performance of edge detection, it needed a lot more error correction, whereas east needed still quite a bit of manual error correction, but it's not ideal, of course. For a fully automatic system, this is not good enough. For a semi-automatic system, arguments could be made. Yes, here you can see the runtime between the two. You see edge detection is 15 minutes and 29 seconds, whereas east is 10 minutes and 1 second. And the average sorter per hour for edge detection is 647.1475, whereas East is able to sort 1,333 cassettes in the same amount of time, or in 1 hour. So how does East specifically compare to the artifact? I don't have time to compare both of them, but East is capable of sorting 54% more cassettes per hour compared to the current way of manually sorting these cassettes, which is a significant improvement, I would say. This will reduce the overall time spent on sorting activities by 35%, and you can see the numbers here. It's quite interesting to see the difference. The graph here shows East on the yellow one, and it shows the current manual sorting speed on the blue pillars. You can also see the table here shows how much time would have been saved. This is an estimate based on the data I've gotten from the lab, but you can see that in 2022 alone, 101 hours could have been saved from sorting activities by implementing East in its current state with manual operation. So you can then imagine what a fully automatic solution would be capable of doing. I think a manual solution would of course be a significant improvement, especially if it keeps the current run times of the current system. So at the end, I will just revisit my research questions and give you a brief overview. I will not go too much in depth as I don't think there is time for that. But so how can the pathology labs be streamlined by implementing automatic sorting mechanism for cassettes? I believe I've shown you how this process can be automated using edge detection and East for cassette recognition, as well as Tesseract for the OCR performance and to read the text. There's also been an improved workflow and system architecture has been proposed, as you saw earlier, and I've talked about how to integrate my project with other ongoing projects at the pathology lab. As for the first sub-question, you can see that the effects of implementing the system is that there will be an increase in traceability, and it will be able to fill in the data which is currently missing from the laboratory information system, which will greatly help other projects, specifically process mining project, as they will have a more fine-grained data set to go through, which will give better results and can allow for better simulations. Yes. As for the second sub-question, I'll just reiterate the statistics I previously showed. You can see that East significantly outperforms edge detection in both of these areas. These are mainly the most important thing, as well as OCR performance and accuracy. I did not know if I stated, but accuracy relates to how many cassettes in an image has been spotted. So if you have 100% accuracy, then all the cassettes in the image is recognized by the system. If you have 50% accuracy, then only half of those cassettes are recognized by the system. So 93% accuracy would say that 93 out of 100 cassettes are recognized by East when scanned. Yes, and for the final research question, again, I will reiterate the sorting speed increases by 54%, which leads to a 35% reduction in the time spent on sorting activities, and this is with manual error correction. I'll talk a little bit about future work and future venues for this project. As you can see, one of the most interesting facts here is to train a custom neural network using the data possibly generated from this artifact. In this process, I've currently used pre-trained libraries for image processing, whereas having a specialized tool for these exact data, I believe, could lead to some very interesting results and hopefully better improvements. However, the current problem with doing such a technique is the lack of data. You would need to require thousands, maybe tens of thousands of cassettes to be able to generate accurate results with these data. However, this application, if put in use for a set amount of time, also has the possibilities to generate this required data. The other improvements which I think can be done is of course get a better camera. I mentioned this earlier. Currently we use an iPhone. It is unideal for these sorts of tasks. A higher resolution camera would not only have more clear text, which would be better results, but it could also take images further away. In our testing, we were limited by roughly 30 to 40 cassettes per image. A full tray is 150 cassettes. If you want to capture all that, you would need a camera with much higher resolution than what we currently use. And also, the ideal solution for this would be a fully automatic solution, one which does not require any sort of error correction. However, this is healthcare data. You want to be very careful. You want to ensure that everything is correct, which is why I believe a fully automatic solution is currently not viable with the technologies proposed here, but in the future it might be, depending on different factors. Here you can see the bibliography for the graphs and some of the images and some of the data directly cited in this